June 3rd, 1997, Brazil against France. Roberto Carlos stands over a free kick, roughly 35 meters out, so far from goal that the defensive wall barely bothers to line up. He runs up and strikes it with the outside of his left foot, and the ball leaves so far to the right that a ball boy standing yards from the post ducks out of the way, and then it comes back. The ball curves through the air, bending back toward the goal, and clips the inside of the far post on its way in. The keeper never moves. Commentators called it impossible. Scientists studied it for years. But here's the secret. That ball never broke a single law of physics. It was obeying something you can't see, the air itself. By the end of this video, you'll be able to see it too. Start with what should happen. Kick a ball and, ignoring the air for a second, only one real force acts on it: gravity, pulling it down. Its path should be a simple arc, up, over, and down, always in the same vertical plane it started in. It should never swerve sideways. And yet, every single week, we watch balls curl around walls, dip under crossbars, and swing away from diving keepers. Something is pushing the ball sideways. There's nothing out there to touch it, except the thing it's flying through. Because the ball isn't traveling through empty space, it's plowing through a fluid, an ocean of air. And if you can make that air push harder on one side than the other, you can steer. Here's how a player does it. When you strike the ball off center, it doesn't just fly forward, it spins. And a spinning ball drags a thin layer of air around with it, like a whisk stirring a bowl. On one side of the ball, that dragged air moves along with the oncoming air, so it speeds up. On the other side, it fights the oncoming air, so it slows down. And here's the key. Where the air moves faster, its pressure drops. Where it moves slower, the pressure stays high. So now there's more pressure on one side of the ball than the other, and that imbalance shoves it sideways toward the fast-moving side. Spin it one way, it bends left. Spin it the other, it bends right. The German physicist Gustav Magnus described this back in 1853, which is why we call it the Magnus effect. A curling free kick isn't magic. It's a player doing fluid dynamics with their foot, deciding at the instant of contact exactly which way the air will push. But watch a great free kick and you'll notice the curve isn't even. The ball flies almost straight at first, and then, near the very end, it dives, as if it suddenly remembers where the goal is. That's real. Off the boot, the ball is moving so fast that its forward speed overwhelms everything else. But air resistance keeps bleeding that speed away, while the spin barely slows at all. So as the ball travels, the sideways push holds its strength while the forward rush fades and the curve tightens right at the end. The bend doesn't happen evenly across the flight. It happens late, exactly where a keeper has the least time to react. Which brings us back to Roberto Carlos. Now you can see what happened. He struck the ball low and on the outside, giving it fierce side spin and enormous speed. For the first 30 meters, the speed won, and the ball screamed to the right of the wall, so far wide the ball boy ducked. But the whole way, the Magnus force was quietly pushing, and the ball was slowing. In the last few meters, the spin took over, the curve snapped shut and the ball bent back onto the post. In 2010, a group of French physicists put that exact goal on paper. They found that Roberto Carlos hadn't broken any law. He'd simply had the distance to let the effect run its course. And they showed something beautiful. Give a spinning ball enough room, and its path stops being a curve at all. It becomes a spiral. Now take the spin away, and things get genuinely eerie. Hit the ball dead in the center with almost no rotation, and there's no smooth Magnus curve to bend it. Instead, the ball's seams take over. As air wraps around the ball, it clings to the surface for a moment and then peels away. And exactly where it peels away depends on where the seams happen to be pointing. Because the ball is barely spinning, a seam can sit in one spot just long enough to nudge the ball one way. Then the ball drifts. The airflow trips somewhere else, and it lurches back the other way. The result is a ball that flutters and darts with no rhythm at all. That's the knuckleball. There's no spin telling it where to go, so it seems to have a mind of its own, and keepers will tell you it's the hardest ball in the sport to read. And if the seams matter that much, then the ball itself changes the physics. In 2010, Adidas made the World Cup ball, the Jabulani, unusually smooth, with just 8 molded panels and very few seams. The problem? That smoothness dragged its wobbly, knuckling behavior right into the range of speeds players actually shoot at. Balls fluttered, keepers grasped at air, and strikers complained. It became one of the most criticized balls the sport has ever seen. The engineers learned their lesson. The ball built for the 2026 World Cup, the Trionda, was deliberately made rougher with more texture and seam, precisely so the air trips in a consistent, predictable way. A soccer ball's design isn't decoration, it's applied aerodynamics, a negotiation with the air. And once you know what to look for, you start seeing it everywhere. A golfer's slice is the Magnus effect. So is a curveball in baseball and a topspin forehand that dips down into the court. Drop a basketball with backspin off the top of a tall dam and it will sail absurdly far before it lands. Same invisible hand. The soccer pitch is just where it's easiest to see, because for 90 minutes everyone in the stadium is staring at one small ball. Spin an object and you bend the air. Bend the air and the air bends you. So the next time a ball bends around a wall and settles into the top corner, you'll know there was never anything supernatural about it. The ball can't see the goal. It has no idea a keeper is diving. It's simply following the air, pushed toward wherever the pressure is lowest. Spin decides which side that is. Speed decides when the curve arrives. And the seams decide how wild the ride gets. A perfect free kick is one of the most beautiful things in all of sport, and it's also just physics, performed at 100 kilometers an hour by someone who probably never wrote down a single equation. On July 19th, when the best players on Earth line up for the World Cup final, watch the flight of the ball. You'll see the air, and once you do, you can't unsee it. If this changed how you'll watch the next free kick, subscribe and tap the video on screen for another one. See you in the next one.